Welcome back, everyone. It's Mrs. Hanson picking up with our Section 5, Enantiomers and Diastereomers. We started considering those structures that are arranged in the same connectivity, for example, a cis-butene and a trans-butene, all containing 4 carbons that are connected to one another, but different spatial arrangements. Since they are stereoisomers, but are not mirror images, we are labeling those with the vocabulary word known as diastereomers. Diastereomers have different physical properties, different compounds, and different names. And the cis and trans are just some of those examples of diastereomers. We see that this difference between enantiomers, which are non-superimposable mirror images of chiral compounds, and diastereomers becomes very relevant when we consider compounds containing more than one chiral center. In a compound with n tetrahedral stereocenters, the maximum number of stereoisomers is 2 raised to the nth power. So let's take a consideration of that. Suppose we have a cyclohexane and we see that there are 2 chiral centers. At carbon number 1, we have the OH group, and at chiral carbon number 2, we have the methyl group. Its non-superimposable mirror images, known as an enantiomer, was simply found by taking each of the wedges and converting it to dashes, an enantiomer. If the first carbon at center number 1 is an R configuration, we know that its enantiomer would be the S configuration. If chiral carbon number 2 that has the methyl is the S configuration, we would then know its mirror image would be R. They are indeed pairs of enantiomers. Notice we just randomly selected the 2 priorities here, putting them both as wedges, making its mirror images both as dashes. Well, what if we go from 1R2S to a new original conformation and change just one of the 2 chiral centers? In other words, we're leaving the hydroxyl group chiral carbon as the wedge, but we are going to change the chiral carbon number 2 with the methyl group, change it from an S configuration to the R. So notice that a 1R2S has had just one chiral center flipped to come up with a 3rd structure. Notice now we have 1R, 2R, and when we draw its mirror image, the dash and wedges will convert and we find its enantiomer. A compound with 2 chiral centers, 2 squared gives me 4 structures that are looking at enantiomers and diastereomers, 4 possibilities of structures, noticing that we have 2 that are non-superimposable mirror images, another set of non-superimposable mirror images, and then the term of diastereomer. Well, if I were to compare one set of enantiomer to another, those are not mirror images at all. They are indeed diastereomers. I could compare the first with either of the other mirror images and come up with diastereomers. They are not mirror images at all. If we consider a cyclohexane with 3 substituents, 3 chiral carbons, we would have 3 squared gives us a total of, oops, I did that wrong, sorry, 2 raised to the n, so 2 cubed gives us 8 unique structures, 2 to the n, where n represents the number of stereocenters. So with 3 chiral carbons, we could have the first all as wedges, and then its mirror image would be all dashes. These are indeed a pair of enantiomers. On this next set, notice we just take one of those substituent chiral carbon branches. There's 3 of them. Let's just take one at a time and flip it, leaving the other 2 as is. So notice the hydroxyl group and the methyl group remained as wedges, and we just simply convert the chlorine from a wedge to a dash. And that's a completely unique arrangement. It was 1R, 2R, 3S. We now are at R, R, and R. Flip the dashes and wedges around for its enantiomer, its non-superimposable mirror image. And there's the next 2 structures. To find a 3rd structure and its mirror image, go back to the original and flip the next chiral carbon. Notice when I say the original, the very first one we drew were all wedges, and now instead of flipping the carbon or the chlorine to a dash, we'll take the second and flip it to the dash, draw its mirror image there, and we come up with a next set of enantiomers. And then finally, to get the next two enantiomers, we go back and take a look at flipping the last, and we came up with 8 unique structures. So when we have 3 stereocenters, there are 8 possible structures, and they're all drawn with us. And we consider these relationships as enantiomers and diastereomers. And this is a very good analogy. Let's suppose that we think of a family where you have 4 pairs of twins, right? Here's a set of twins 1, 2, 3, 4. Enantiomers are non-superimposable mirror images. In essence, they're twins. I'm seeing a reflection in the mirror, and it looks a lot like me. That's a twin. But you have a total of 8 kids. So each kid has 7 siblings, whereas one of them is their enantiomer, that's their twin, and all others, the 6 others, would be their diastereomers. They do not look like one another in the mirror at all. So a set of twins gives you, for this structure, 1 enantiomer, and all of the other remaining siblings, if you will, would be diastereomers. They're not mirror images. So as we practice identifying whether each compound, each pair here is an enantiomer or diastereomer, and you have kind of some choices here of really how to tackle it, but let's kind of just understand what we're being asked to do. I have a compound, and I notice that there are 3 chiral carbons. 1, and then I have another here, and then another here. Those are the 3 chiral centers. In order to know if these pairs are enantiomers or diastereomers, we know that we would have to look at the mirror image of that compound and then compare it to see, and this is kind of just a strategy, select the first structure, invert all the chiral centers to create its enantiomer. And does it look like the other structure? If not, then they're not mirror images. They would be diastereomers. So I'm going to draw this particular structure and invert the first chiral center to be the wedge of OH. This would also become a wedge leading to the methyl back down, and then of course this becomes a dash to the OH. So just to repeat, my strategy is I invert all chiral centers to get its mirror image. So these two are known as enantiomers. I took all of the dashes, converted to wedge, and I took the wedges and converted to dashes. Now we just compare to this structure. I notice when I compare that when I examine the first chiral center, that carbon leading out to hydroxyl, that's a match. It leads out as a wedge. Even when I examine the next chiral carbon, it comes out as a wedge as well. But I notice a point of difference right here in the third chiral carbon. The third chiral center is leading out to the OH as a wedge in the structure, but when I drew the mirror image, it was a dash. So therefore, these are not the same structure, they are not mirror images, and therefore I am labeling those as diastereomers. When we draw the mirror image, I'm simply going to check and make sure that I have a structure that matches the other, and clearly we see that we do not. Diastereomers. You have plenty of those to practice. Are these the same, or are they diastereomers? Well, sometimes, when I think about drawing a mirror image and trying to find if it matches or not, that's one strategy. But I also want to encourage you, as another strategy, is just to consider the R and the S configuration. And what I'm saying is, if you determine R or S configuration for clockwise spin or counterclockwise spin, the enantiomer must have the opposite spin. So with this particular example, I notice that there's a chiral center here and a second chiral center here. What happens now is when I have redrawn this, what became a little unusual is, notice that we've had kind of a movement of the carbon chain. So at this particular chiral center, the methyl group and the butyl group have switched places. So I don't know necessarily if they're mirror images or not. It's a little bit more difficult because the attachments changed. And so instead of considering, just inverting dashes and wedges, it won't work on this example because the substituent branches have changed location. So what I'm suggesting is, as an alternate method, when that happens, just assign R and S configurations. So here I know that it's not shown, but we know is a hydrogen coming out as a wedge. Priority number 1 here would be the long chain carbon. Priority number 2 would be a second chain carbon. Priority number 3 would be the 1 carbon chain. I know that when I connect those numbers, 1, 2, 3, this gives me a clockwise spin, but since the hydrogen is a wedge pointing out at me, I have to walk around to the other side of the molecule, so I really have to flip my answer to a counterclockwise. Priority 4 is a wedge, so I know to flip. And that's how we come up with an S configuration as shown in this example. Now let's do the same strategy for the second chiral carbon. I'm going to erase this work. We've labeled this first one as S. How about this guy here? Top priority, let's see, 1, 2, 3, 4 carbon chain. Here, though, is a carbon attached to more carbon. So this will be priority 1, then priority 2, then priority 3. Remember that the hydrogen is still a wedge. So when I connect, I'm going in a clockwise fashion, but since the highest priority is going behind the page, the hydrogen's coming out as a wedge, that tells me I have to flip. So I go to counterclockwise, and this is also an S configuration. So with my first configuration, we've determined an S, S at those 2 chiral centers. Now we know to be an enantiomer, both of these chiral centers would now have to be R, R. And are they? I mean, that's what we have to test. Again, this guy is a chiral carbon. We said that the highest priority would be in the direction that leads to the more carbon in that point of difference. So 1, 2, 3. It is spinning now. Remember, with the hydrogen is in the back, which is what we want. And so when I spin hydrogen in the back, we leave it as a clockwise spin. That is indeed an R configuration. Let's try for the next chiral carbon. That's this guy. And when I think about priorities, the carbon that's attached to more carbon is top priority, then 2, then 3. Remembering not shown, but coming out here would be the hydrogen as a wedge. So when I connect my numbers, I see a counterclockwise spin, but since hydrogen's the wedge, I have to flip my answer, and this becomes clockwise R. So we have indeed proven with the examination of the R and S chirality system that an S, S has indeed flipped to an R, R, and therefore I now know with confidence they are enantiomers. If we started with SS and ended up with an R, S or S, R, or for heaven's sakes, if they stayed the same, we would know that they are not enantiomers. So a couple of ways to approach those problems. Let's introduce a little idea about symmetry in a molecule that contains a chiral carbon. Any compound with only one chiral center will always be a chiral compound. It gets a little messier if we have more than one chiral center and the compound may not be chiral because there's a plane of symmetry and therefore the reflection becomes superimposable. Consider these two structures. They both possess two chiral centers. These are stereoisomers, which possess two chirality centers. One, of course, would be where the methyl groups are one above and one below the plane of the ring. So that's the trans configuration. And here we would have where both of these are in the above plane, so they're in the cis configuration. Think about a plane of symmetry in this molecule. If I think of a plane of symmetry and kind of putting a mirror halfway through the molecule and asking the mirror to reflect upon itself, do you see with the cis configuration a complete plane of symmetry? The cis isomer, because it has a mirror image within its own structure, notice that as I put a plane of a mirror right through the center of that molecule, everything is reflecting back exactly in the same position as the original side. So the left reflects the right side. That's a plane of symmetry in the molecule, and therefore it is now considered to be achiral. There are two chiral centers, but the molecule is achiral because within its own structure there is a plane of symmetry, making the molecule superimposable with its mirror image. And that breaks the rule about being a chiral compound. It has to have an enantiomer, a non-superimposable mirror image. So even though the cis configuration contains two chiral centers, the molecule itself is said to be achiral. So when we have more than one chiral center, we have to examine if there is indeed a plane of symmetry making that compound achiral. These molecules with even number of chiral centers, just like we examined an even number as 2, they have planes of symmetry, are called Meso Compounds. A way to test if a compound is meso is just to identify its mirror image. Draw the mirror image of the cis isomer and show that it can be superimposed, and that's what we've done here. As you think about superimpose, find that plane of symmetry, and this now has proven that since this exists in a complete plane of symmetry, it is a meso compound. It is achiral. That compound is identical to its mirror image, and therefore, since it cannot have an enantiomer, it's not chiral. So if we have a plane of symmetry, it is achiral. However, there's yet one more possibility of a compound with chiral centers, not necessarily having a plane of symmetry, but has a point of inversion. This is another unique set of, just something else to consider that would make the molecule achiral overall. I want to examine what I mean by a point of inversion. The molecule to the right has two chiral centers. Let me find them. A chiral center has two of them. So is this chiral or an achiral molecule? Well, instead of being able to place a plane of, like an actual mirror and cut the molecule in half and see your mirror image, I want you to stand right smack in the center as a point of inversion. You notice when I look up, I have a methyl group as a wedge. When I look down, I have a methyl group as a dash. They have inverted. When I look this direction, I see nitrogens. When I look in this direction, I see those carbonyl carbon-oxygen bonds. This point is giving me a mirror image, reflecting about a point rather than an entire plane, but this makes the molecule achiral. There is an inversion point where these two chirality centers have no plane of symmetry, but it's still achiral because of this inversion. The methyl at the top reflects to the methyl at the bottom. Notice the dash became the wedge and vice versa. The oxygen to the top left reflects the oxygen to the bottom right. And nitrogen to the top right is reflecting to the nitrogen bottom left. That is a symmetrical inversion, which makes the molecule achiral. So just some, things to consider when we have an even number of chiral centers. Check to see if you have a plane of symmetry. If so, it is a meso compound, which is achiral. Check to see if there's a point of inversion. If so, it is achiral. Otherwise, we go through this 2 raised to the n tells me how many stereoisomers a compound has based on the chiral center, unless there's a meso or an inversion to consider, and that eliminates the choice. So kind of thinking about symmetry and chirality, the presence or absence of a rotational symmetry is irrelevant to chirality. A compound that has a plane of symmetry is achiral. We call that a meso compound. And a compound even without a plane of symmetry is usually chiral unless there is an inversion center. Stand in the center of a cyclic structure and see if you have an inversion point, which makes the molecule achiral. Not often, but we're just saying there are some exceptions to consider. So as we think about meso compounds, compounds with 2 stereocenters sometimes may not have 4 stereoisomers since molecules are achiral. So even though they have these chiral carbons, sometimes we don't end up with 4 stereoisomers. So let's examine an example here. So here I have a 1, 2, 3, 4 carbon chain and 2 chiral centers. Notice that they're both coming up out of the plane, so we call that a cis configuration. I draw the mirror image and I end up with one that's a dash and the other is a dash. These are a pair of enantiomers, non-superimposable mirror images. Now remember, I could have drawn the mirror image. Doesn't matter. This could be also the mirror image. Here's your OH. Here's your BR. Your mirror image could have also just been this, right? You could have just drawn back what you saw in the mirror. Those two are exactly the same structure. Just kind of saying one method of finding an enantiomer is just to take both chiral carbons. Here, remember, the hydrogen is a dash. Here, the hydrogen is a wedge. And we just made all the dashes turn into wedges and vice versa. Or you could literally draw a mirror and see what the reflection is. Either strategy works perfect. Notice here now, we've just taken one of the 2 chiral centers and flipped the direction. So we had a trans configuration and drew its mirror image. These are a pair of enantiomers, non-superimposable mirror images. So here we worked perfect. 2 chiral centers means 2 to the nth, 2 squared gives me 4 stereoisomers. Perfect. We know that these 2 are a set of twins, enantiomers. These 2 are a set of twins, enantiomers. Therefore, any other combination would be diastereomers. These 2 are diastereomers. These 2 are diastereomers, and so forth. So this family with 4 children, 2 sets of twins. One twin has 1 enantiomer and 2 diastereomers. Kind of thinking through that. Now, let's examine a different picture. Notice now, instead of having 2 different functional groups like a hydroxyl and a bromine, I've now made them the same. These are both chiral carbons. They're both leading to 4 different substituents. However, the substituents are the same on chiral carbon 2 and 3. They're both leading to bromines. And so think about, when I have 2 wedges and I will simply walk around to the other side, I still have the same compound. These are the same compound, so therefore this is a meso. Notice there is a plane of symmetry. The trans produces enantiomers, but there is no enantiomer for the cis configuration, so now all of a sudden we only have 3 stereoisomers for that particular compound. 2,3-dibromobutane has only 3 stereoisomers because there's a plane of symmetry in the cis configuration. So the cis 2,3-dibromobutane is a meso compound. It is not a chiral compound. There are 3 stereoisomers, 2 pairs of 2 structures that are enantiomer and 1 diastereomer. A compound with chirality centers that it's achiral, we're learning to call it a meso compound. And this is where you're going to just practice with your skill builders 5.7. If you can find a plane of symmetry, you know to recognize that as a meso compound. And so here, this didn't copy and print very well, but this right here is a cyclohexane. Both of these are coming out as wedges. I can clearly see a plane of symmetry, making this a meso compound. Here again, I have a plane of symmetry, making this a meso compound. And right here, I still have a plane of symmetry, making this a meso compound. So looking for a plane of symmetry, when you examine whether each of these chiral carbons would produce a new set of enantiomers. When we think about writing meso compounds, and are we going to have two sets of twins or only one set of twins with a diastereomer? That's kind of the goal. Let's practice with 2,3-dichlorobutane. Write all the possible formulas for the stereoisomers and then just label them as enantiomers or meso. So the strategy here is I just want to redraw that butane, 1, 2, 3, 4, and I'm just going to randomly place the chlorine, and I'll put the hydrogen as a dash. We don't need it, but we know it's there. And I'm going to do the same up here. Here's the chlorine, and here's the hydrogen. There's one possible stereoisomer for that particular 2,3-dichlorobutane. When we draw its mirror image, I'm going to flip the dashes to become wedges. Here's a chlorine. Here's a chlorine. Alrighty. Now, I'm going to flip just one of those, and let's keep this guy a wedge, but let's make this guy the dash. That's a third structure. And then its mirror image would have chlorine coming out with the dash here and the wedge up here. Don't need them, but I'll place them in. So what do we have? So first of all, I notice that when I have this configuration where I have one dash and one wedge, these truly are enantiomers. Non-superimposable mirror images, and I can spell enantiomers. There is no plane of symmetry in that molecule, simply because when I have one chlorine as a wedge, the other as a dash, they're not going to reflect in the same way. But look at this guy, when they're both dashes and both wedges, these are exactly the same molecule. Think about it, when I put a plane, a plane of a mirror there, it's reflecting back with the identical image. You're really just walking around the molecule. If both are wedges and you walk around and examine it from the opposite side, now they're both dashes. So these are indeed the same molecule. So this is what we would refer to as a meso compound, and these down here would be known as enantiomers. There are 3 unique structures, stereoisomers. 2 are enantiomers and 1 is a meso compound. There is a plane of symmetry. So what we did there was to draw one, then flip both centers, and now you have enantiomers. When we drew again, we flipped just one chiral carbon, and when you examined that, we did recognize a plane of symmetry and found a meso compound. So that's what you'll practice when you're looking at your meso examples, looking for a plane of symmetry. You will have an opportunity to look for points of inversion as well. I'd like to draw with you yet another opportunity to represent three-dimensional molecules on a flat piece of paper with something that's so easy, something that you're going to just fall in love with, known as a Fischer projection. We often use Fischer projections when they have compounds that have multiple chiral centers, and they just make it so easy to compare enantiomers and diastereomers. So let's get involved with a Fischer projection. Knowing that the horizontal lines in a Fischer projection are coming out of the page, and the vertical lines represent attachments going behind the page. So we're going to see these crosses for Fischer projections. All right, and this represents the chiral center and the four things that it's attached to. When I look up and I look down, those are known as the vertical lines. They tend to be the carbon chain. So we like to place the carbon branches, you know, the long carbon chain, in the vertical line. If we have chiral center functional groups, they'll go on the horizontal line. So I'm going to look left and look right. We call those horizontal lines, the horizon. And that's where you'll find your functional groups. So with this molecule, here's a 2-carbon chain. Here's a carbon that's in the center, and then one more carbon that's a methyl group. At the chiral center, I see that we have a hydroxyl group. And of course, the fourth attachment would be a hydrogen. So notice this is the chiral center. This is nothing more than 2-butanol. Drawn with the Fischer projection, we make this carbon, the chiral carbon, the center right here of the cross. Alrighty. And then when I look up, down, left, and right, remember how I wanted the carbons in the same line? They become the vertical branch. So when I write ET, that's going to represent CH2CH3. And on this side, the going down in that vertical would represent the methyl group, CH3, and you can see that written as Me. Now, you're just looking at this from a different vantage point, right? And so think about this in the terms of the branches here. If I had originally the hydroxyl group coming out of the page and looking at the hydrogen here, to get these vertical lines, you're just changing the vantage point so that these carbons are all in the same plane. And to do that, you just twist the molecule and kind of examine it from this angle, where priority 1 and 4 are coming out of the page. They're coming out to hug you, is what I like to think about it. 1 and 4 reaching out to hug you. And notice 2 and 3 then go behind the page. And so when we represent that, if 1 and 4 are hugging you, they're wedges. 2 and 3 are hiding from you, those are now the dashes. So we just envision the dashes on the vertical and the wedges on the horizontal line. View to put the longest chain away from your eye, and usually the most oxidized carbon, the one with most oxygens, you can also say that the least hydrogens, is at the top. And so if I have for example, lots of oxygen on a carbon, that tends to be placed on the top of a Fischer projection. Notice I want to keep the carbon in the vertical line. The carbons that have lots of oxygens attached tend to get placed up high. Carbons with the least amount of oxygen, or you could say carbons with more hydrogens, are attached towards the bottom. Horizontal lines come out of the page towards you. Remember, these are coming out to hug you. Those are the wedges, little bow tie, and then hiding behind are now the dashes. But isn't this so much easier? Drawing a little cross, that's a chiral carbon, and we'll just simply tell you based on the priorities where they fall. So this would be like priority 1, 4, priority 2, 3. When we get going, and you're just going to fall in love with these, how easy they are. So these Fischer projections, oh gosh, when we use complex molecules, like really big sugars, for instance, when we study carbohydrates with multiple chirality centers can very easily be drawn just by looking at the number of crosses in a Fischer projection. Here I can see 2 chirality centers, 2 centers of the horizontal and vertical lines. Here I'm recognizing 3 chirality centers because I'm seeing 3 crosses of the horizontal and vertical lines. 4, right here, 4 chirality centers. And what makes this so nice is how easy it is to find enantiomers and diastereomers, because enantiomers are mirror images. So with these 2 chirality centers, if bromines are placed on the right, its enantiomer would have them both placed on the left. It is indeed a mirror image. Notice here, if the structure had both bromines on the right, and we now all of a sudden have something going on with one right, one left, that's not a mirror image. So quickly we can recognize those as diastereomers, non-mirror images. Very easy to draw and recognize enantiomers from diastereomers. So kind of some considerations about Fischer projections. We are allowed to rotate a Fischer projection by 180 degrees and not change the identity of the molecule. So if I were to take this compound here, if I take this compound and bring the, the COOH down, the methyl group would come up and everything just shifts by 180 degrees. That is completely the same compound. What you're not allowed to do is to shift only 90 degrees. So I can't take this COO and make it now become on the vertical axis. If it's vertical, it can't go on horizontal. If it's on horizontal, it can't land at the vertical. So I'm allowed to change 180 so that I keep all of those ingredients that were on the straight line up and down vertical, and I have to keep the HOH here on horizontal. I'm really just twisting the molecule 180 degrees. But I'm not allowed to just twist it 90 degrees because you've now created a different inversion. It's not the same orientation. So to determine a configuration on a Fischer projection, this is actually quite simple as well. Remember that the horizontal lines are wedges, and that the verticals are dashes. We're just going to select one of the horizontal and make it a wedge, and we'll select one of the two verticals and make it a dash. And it absolutely does not matter which one of those you turn into the vertical line as a dash or a horizontal as the wedge, because you're going to get the same answer either direction. So for instance, here's a Fischer projection. This is a chiral carbon. It's the same chiral carbon in all four of these structures. Alrighty. Now I have two choices to be wedges. If I take the first choice and make the hydroxyl group the wedge, then hydrogen stays in the same plane. Or as the second choice, I can make hydrogen the wedge and leave OH in the same plane. I just pick one or the other, it does not matter. And in the next decision, I have two choices to make the dashes. I can make the dash the CH2OH, or I can make the dash the COO. It doesn't matter, I just have to pick one. They're all the same, and you're going to get the same answer regardless. Alrighty? So then we just assign priorities, just as we've always done. But what's interesting, okay, let's kind of go through. Here's a carbon attached to lots of oxygen. Priority 1, of course, is going to be carbon directly attached to OH. Priority 2 would be the carbon attached to most oxygen. Priority 3 is going to be the carbon attached to more hydrogen. And when I spin this direction, we get a clockwise spin. Nope, that's a counterclockwise spin. But remember, the hydrogen is a wedge. So that means we flip our answer, walk around the other side, flip the answer, and you get a clockwise spin. This is an R configuration. Now I determined this to be R. I randomly picked that structure. Let's confirm to ourselves we get R no matter which way we pick. So again, priorities are the same. The priority here, we would still number as 1, then 2, and then priority 3. When we spin, we get a counterclockwise configuration, but because the hydrogen is a wedge, we know to flip, and it becomes clockwise, so we still got an R configuration. So this is the R configuration no matter which direction or which one that you choose to make your configuration from. And you're just going to practice with those. Identify as an R or S configuration in the following Fischer projection. So as you redraw this, here's your chiral carbon. Here's the carbon here, and I'll just make the NH2. And let me just start by reminding you what we're really looking at. So I'm going to remind you that both sides can be considered wedges, right? So, and I guess that's even easier. I'm trying to draw this and get out of that screen. There, I got it. Thank goodness. Here's the chiral carbon. I'm going to make this guy, the hydrogen, is the wedge, leaving this guy in the same plane. That makes this guy a dash, leaving this guy in the same plane. All right, that's really what you're deciding. It absolutely doesn't matter if you take the dash just top or bottom, pick one. Absolutely doesn't matter if you take the wedge as the left or right, just pick one. Assign priorities. The highest priority would be the nitrogen. Lowest priority, of course, is the hydrogen. The carbon attached to most oxygen would be next. Here's the hydrogen, the carbon attached to most hydrogen. When we spin, we get a counterclockwise configuration, but the hydrogen was a dash. Priority 4 is coming out of the page, so I flip. This ends up to be a clockwise configuration. This is an R chiral center. Let's try another. Here's a chiral carbon. I'll make the hydrogen over here as the wedge, leaving the OH in the same plane. I'll leave the carbon, oxygen, that's an aldehyde, C double bond O to H going up, meaning this then becomes the dash, and that's a methyl group. Assigning priorities, of course the oxygen would be top priority. Then the carbon attached to oxygen would be second priority. And of course the methyl group would be third priority. And we connect the numbers. This time, 1, 2, 3. This gives me a clockwise spin, which is R. But since hydrogen's a wedge, we know to flip our answer. And we come counterclockwise. This is an S configuration. You did it. The last part of our topic in our lessons are going to convert E and Z designations when naming alkenes. And this is placed into this chapter because I know alkenes give us stereoisomers. Remember, that's our topic, stereoisomers. And this is an example of a stereoisomer when I have a double bond. So far, we've examined a cis-trans configuration of double bonds. And just to remind ourselves, if I have an R group on whatever that alkyl group might be, and I have two identical groups, two things that I can compare that are the same, such as these two hydrogens, I can now call them cis or trans. I know that if I have two hydrogens on the same carbon, that there's no such thing as a cis or trans. So we're learning to examine, looking left and looking right, I have to have two unique groups, right? I have to have two different things to assign cis and trans. And of those left and right, two of them have to be the same, two of them have to be different. Okay, so that was practiced. Cis and trans only works if there's a like group on each carbon atom in the double bond. And that's what I'm emphasizing here, a like group. So if I have two hydrogens, I can find cis or trans. But if I don't have two of the like groups, and I mean the two carbons in the double bond have to have something the same of those four attachments in order to make a cis-trans work. A cis-trans, if I have two chlorines, those are the same. That can have a trans configuration or a cis configuration. As long as two groups are the same, when I have a look left, look right, the two carbons in the double bond have to have two like attachments in order to compare a cis-trans configuration. But what if they don't? What if they have more than, different types of attachments leading out from the two carbons in the double bond? Here's an example of that. Here is an alkene. This carbon-to-carbon double bond is what we're examining. I notice that we have 4 unique attachments. We have an NH2 group, which is very different than a hydrogen group, which is very different than an ethyl group, 2-carbon unit, which is very different than a fluorine group. 4 different groups. And yet I can see it has a stereoisomer. I can see that a different configuration, these are diastereomers, are not mirror images. I notice that on this side, whoops, I wanted yellow, that I still have the ethyl group, that's the same. There's a 2-carbon unit. I still have the fluorine group in the same position. So on the left side, I still have yellow top. Fluorine is on the bottom. I color-coded orange. But now over here, the nitrogen flipped to the top side and the hydrogen flipped down. And remember, that's not by rotation. Double bonds cannot rotate. So these are not mirror images. They are diastereomers. How do we give these names that are unique from one another? And that's what the EZ system is going to allow us to do, the EZ system. We are going to assign priorities, just like we did for the RS configuration. We'll assign priorities based on atomic numbers. For each of these carbons, we're going to examine the left side and the right side and examine who has higher priority. So let's stand at this very first carbon. Who has the atomic number that's higher between a fluorine and between the carbon? Well, of course, fluorine does. It is of higher priority. So the fluorine is at the position of higher priority based on its atomic number, comparing it to the other attachment of the carbon in the double bond. So I'm comparing this carbon's 2 attachments and assigning a priority. Let's do the same over here. Here's the carbon, the other carbon in the double bond. Let's look at its 2 attachments and decide who has higher priority based on atomic number. And clearly you see a nitrogen is of higher priority, of higher atomic number than a hydrogen, who's always low priority. So we have the configuration where the 2 carbons involved in the double bond are placing the higher priority below the plane of the double bond, below the plane in the same direction. We're going to learn that the same direction is going to be given a Z conformation designation. I'll explain what that stands for. And on this side, here is the plane of the double bond, and these are on the opposite side. Higher priority are on the opposite sides. If they were on the same side, they were given the Z configuration. If they are on the opposite sides of the plane of the double bond, they get the E conformation, opposites. Let me reinforce that. Assigning an E or a Z configuration to a double bond allows us to compare stereoisomers that are diastereomers, that means they're not mirror images, and give unique names to these compounds. We said we examined the 2 carbons that are in the double bond. So I'm just going to look left and right, the 2 carbons that are in the double bond. In one direction, it leads to a carbon. In the other direction, it leads to a fluorine. Fluorine is of higher priority. Do the same over here. Here's the other carbon in the double bond. I look up, I see a hydrogen. I look down, I see a nitrogen. The nitrogen is of higher priority. When I assign the higher priorities and notice that they're both down, the priority groups are on the same side of the double bond, it gets a Z configuration as part of its name. Now Z stands for zusammen, meaning together in Greek. If the top priorities are on opposite sides, it gets an E for antigen, which means opposite in Greek. Now here's my clue. Z, to me, I can remember saying it's the same side of the molecule. The Z designation, if I notice that the top priorities are on the same side of the pi bond, a Z configuration, because I remember Z configuration from saying, oh, that's the same side. The other way that I can remember is if the priorities are on the opposite side of the plane of the pi bond, E gets its designation. E and opposites both start with vowels, and that kind of helps me notice E and O are both vowels, opposite sides, and Z for same helps me remember that that's the designation for the same side. EZ conformations. And so if I were going to name this, Z just simply becomes part of the name for that conformation, or the letter E becomes part of the name for that conformation. Just like we included R and S for chiral centers, we're now going to include E or Z when we name alkenes that have stereo conformations. So let's work through an example. Identify the configuration of the following alkene. We're not being asked to name it, but we want to just know what are the stereocenters and if it's an if it's an E or Z configuration. Well, I notice I have two double bonds, so I have to examine two possible considerations. So my first observation says I have double bonds located for the first one here and the next one here. So if I'm learning that EZ designation relates to double bonds, let's first look for the double bonds. Now, one of the things I also notice down here is that this carbon in the double bond is leading to two like groups. Both of those are hydrogens. So therefore, that means that it has no stereoisomer, because they have to have different groups. So when I have two hydrogens, two methyls, two anything that's the same, there is no such thing as cis-trans. There is no such thing as an EZ configuration that has no possibility for stereoisomers. And why is that? Well, think about it. If I take the H and switch places with the H, I create the exact same thing. They have the same priority, don't they? The same exact molecule, same priority, so no stereoisomer. Well, that was fun. I can just take all of that consideration off the plate now, because that green highlighted bond does not have a stereoisomer. So therefore, I cannot name it as an EZ or even a cis-trans. However, we can look at these two carbons, and that's what I want to do first. I'm going to look at the attachments on either side of the double bond. Let's examine what I'll highlight in purple first. Let's do this guy. So here I have a carbon. Here I have a carbon. So I need to identify a point of difference. Both of the carbon here that I colored purple are leading out to carbons. This carbon is attached to two hydrogens and an OH. This carbon is attached to three other carbons. So clearly I see the higher priority would be the OH group, because oxygen is of higher priority than carbon. So on this side, I'll make it purple. The priority group is pointing up above the plane of the double bond. So remember, I'm giving priorities up or down of the double bond, but to assign priorities, I look at one carbon at a time. So let's examine the next carbon. Here we have, just kind of thinking here, no point of difference yet. That's both CH2. Go to the next carbon. Ah, there is a point of difference. This carbon is bonded to more carbon, making it higher priority. And so I'll highlight that in blue. When I examine for priority, I'm looking at both attachments on the same carbon in the double bond. I'm looking left and right, right? But now, all of a sudden, when I want to know if it's E or Z, I want to compare the priorities to the pi bond. So I look this way. Carbon number 1 of the double bond has its priority pointing up above the plane of the pi bond, and this carbon number 2 of the double bond has its priority below the plane. So that's opposite sides. Whoops. An opposite would get the vowel, right? The E configuration. So as we examined those, we found the opposite sides giving it an E configuration. Examine the first carbon in the double bond. The priority lies to the top. Examine the second carbon in the double bond. Its priority lies to the bottom. The opposite sides is the E configuration. And you'll have some practice with E versus Z, the same side or the opposite sides of the pi bond. And you have made it through your Stereochemistry, Chapter 5. Good luck with your homework, and I'm here to support you.